Okay, welcome to today's sustainability seminar. My name is Nancy Holm, as many of you know here, and I'm the Assistant Director at ISTC and Seminar Organizer along with Beth Muszewski. We have the schedule for the rest of the semester and flyers about the upcoming seminars out on the table outside here in the conference room, and then also they're listed under events on our website. And as many of you also may know, that if you can't attend in person, all of the seminars are broadcast live via GoToWebinar and also are recorded and archived on our website. We've had some delay in putting the last few seminars up on the website, but we hope to have those up there soon. I also want to welcome anyone listening to this broadcast today. So to begin, I'd like to ask the people here in the room in attendance to please silence your cell phones. And also we'll hold all of our questions for the speaker to the end, and I'll come around with the microphone so that we can record those questions too. And then for those viewing online, you can type your questions in at any time, and we'll answer those at the end of the presentation also. So we're very pleased today to have as our guest speaker Dr. Sudhira Brahmbhatt, who is President of Technology Services Incorporated in Glencoe, Missouri. He brings to us a wealth of knowledge in the environmental, chemical, pharmaceutical, biotechnology, and metals industries for industrial gas applications. He's an inventor, and he has over 25 patents in this area. He has brought a couple of his devices today to show. He has over 35 years of industrial experience with a number of companies, including Exxon, Air Products, Messer-Gressheim, and Air Liquide. He has co-authored papers in chemical engineering and ceramic engineering, Cryo Gas International, and also ALCHE Journal of the American Institute of Chemical Engineers. Currently, he's a consultant for a range of industries, including top industrial gas manufacturers, chemical companies, and universities. So today he's going to be presenting a talk on applications of gases for environmental issues. Please join me in welcoming Dr. Brahmbhatt for his presentation today.
Thank you very much, Nancy. I appreciate that. And thanks for giving me the opportunity to come out and speak to you guys. My focus today is to look at industrial gases. Industrial gases means oxygen, nitrogen, hydrogen, helium, argon, krypton, CO2, and how they're used in the industry. Over many years, I've spent time in applying these gases as chemicals to a variety of industries, and I'm going to touch on some of the applications and look at, my focus will be more on environmental area, and what I found is these gases impact tremendously on productivity, yield, and economics. I'll quickly go through some of them, and if you have questions, let me know later on. We will talk, and if you have a specific interest in a specific area, we can talk on one-to-one basis. I want to cover basically company, what I'm running, and also what are industrial gases, how they're manufactured, just quickly touch on that. And I want to focus on oxygen use in pharma and biotech area, then environmental industry. Remember, the whole focus is how we can improve the environment. Also look at the high temperature applications and wastewater treatment. I'm going to go through each of them quickly. The company, what I founded and what we have is the main focus here. Did I do something wrong? Okay. The company which I have is our focus has been on variety of industries: chemical, metal, environmental, pulp and paper industry, pharma, and cryogenic applications. Main focus has been as to how do we make it economically attractive and environmentally safe. Our services include supporting all these industries. How do we improve the productivity or yield increase? And we're basically located in St. Louis, Missouri area, and that's on the website. Quickly look at as to industrial gases, how they're manufactured in the industry. If you, how do I use the pointer here? Pointer, the bottom one for pointer? Oh, time. Okay, if you look at Joule-Thomson principle, which states that if you compress air and expand, it cools down. The same principle used here in manufacturing industrial gases. You compress air to the extent that your final temperature is close to minus 400 degrees Fahrenheit. Then air is liquid. Liquid air is going through the distillation column, and based on boiling point of these gases, you're separating out nitrogen, oxygen, argon. This is how industry manufactures industrial gases. Many times, from economics purpose point of view, they build these air separation right close to use point where they have a large amount of these gases being used, like nitrogen, oxygen. And they will make additional product to liquefy in the liquid form, nitrogen or oxygen, and they will sell what they call merchant gas. Means in the merchant area, within 120-mile radius, they will sell these products. That's economical. That's why the 120-mile radius comes into play. Oxygen manufacture, again, you're looking at it as a non-flammable. It supports the combustion, heavier than air, and used in a lot of industrial gases application. Nitrogen, again, is used in a variety of areas. We'll touch on that quickly. And argon is also, when you have requirement for inerting and blanketing and things like that in chemical reactions, it's used widely. They refer the term A100 and L200. A100 refers to, they will say, well, we have ASU, A100 plant. That means 100 tons per day of oxygen, 100 tons per day of nitrogen. When they say plant as a L200 liquefier, then you're looking at 200 tons per day of liquid products. That's the industry term they're using in the market. It's too much in this particular slide, but I'll just quickly mention about this. Oxygen and cryogenics, which refer to nitrogen areas. You're looking at its application is in the environmental area, fish farming, clay industry, combustion, and chemicals. Very quick summary on these I have put together. Gases used are nitrogen, and all these different gases are used. And these are industries which use these gases for different purposes. Let's look at particularly pharma and biotech industry. There are two focuses. One is to improve the environment, and second focus is improve the yield and productivity. When we say productivity, means in shorter time produce the same product. Yield means given how much food we give to organism and how much final product they make. Amount of final product made from the same amount of glucose that they put in, that's the yield we are referring to. So you're looking at in this particular area, we're looking at increased bacterial life, attractive yield, significant reduction in exhaust volume. This is the impact on the environment. If you see most of the aerobic fermentation processes, you will see large amount of exhaust coming out. That's the 70–80% is basically nitrogen. Remaining is ammonia and a lot of other components in there. By using this process, you're able to basically cut down significantly the exhaust volume. We have an example right here in the Midwest region that company is already doing all that stuff and are patented in these areas. And also, if you're familiar with what is lag phase and the growth phase and stationary phase, this is a typical cycle. When organisms are moved from seed media to actual manufacturing, they have a certain time period where organisms have to settle down with a new environment. That's called lag phase. They don't produce during that phase anything. They just basically get used to the new environment. And then there's a significant growth in bacteria. And then the stationary phase and the death phase. There are certain areas where oxygen demand is very high. When you put pure oxygen, that's what we did, pure oxygen in this particular area. And we saw significant improvement in living organisms' life and also productivity and yield. This is simple model simulations, what we did. If you look at that typical base case, people use air in aerobic fermentation process. Let's say, for example, you have 100 cubic meter per hour airflow in there. And you have oxygen concentration, typical air, 21% oxygen, 79% nitrogen. And you have agitation system in the aerobic fermentation system. And this is RPM, this is power usage, and this is a critical part as to percent increase in oxygen transfer from what you put in gas phase to liquid phase. This is the quantity. When we go with increase flow. That's the one method people increase the oxygen dissolution in the media. That's the one way to do it. Yeah, you increase almost to 15, 16% oxygen dissolution into liquid phase. When you increase the RPM, that's another way to increase Reynolds number, NRE, that allows you to also increase your oxygen dissolution. It was close to 72.4% increase in oxygen transfer into the liquid phase. When we went with pure oxygen, we kept the same flow rate as before, but no nitrogen, just pure oxygen. You can see close to 400 times more oxygen dissolved in the liquid phase. We looked at that oxygen, you don't need that much oxygen, so we tried typically what we put before in 100 cubic meter per hour flow, but 100% of oxygen, only 20 cubic meter per hour. Still 88% increase in productivity. What that states is to when you use pure oxygen, if you look at the partial of oxygen in the liquid phase and with the nitrogen, when you don't have nitrogen, a lot more oxygen is dissolved in the liquid phase. The rule of thumb is 5 times more oxygen is dissolved in the liquid phase when you use pure oxygen. Otherwise, normally when you have at ambient pressure temperature condition, you're dissolving about 7 to 8 ppm of oxygen. With pure oxygen, you can 40 to 50 ppm. Excellent approach in a variety of liquid phase operations, whether it's chemical reactions, wastewater treatment, or pharma and biotech industry. This is one simple, this is actual test, by the way. We are done with some company in the Midwest region, very huge company here. If you look at that efficiency, oxygen transfer rate, we looked at with air. You can look at that the way, the trend shows. Maximum was about 13, 14% and went down. So if you look at the average, somewhere around 7 to 8% transfer. When I look at the pure oxygen, very interesting chart here, up to 180% efficiency you're looking at. You can look at how much oxygen went into the liquid phase oxygen transfer in the pure oxygen trial. You can look at on average is somewhere around 40, 60%. This shows itself as to amount of oxygen dissolved in the liquid phase with the media or wherever you're using it. It really significantly goes into the liquid phase. What are the applications? You're looking at variety of fermentation processes. When you look at antibiotics or enzymes, vitamins, what you're looking at, bold letters here, these are the places where oxygen finds its home to increase the productivity yield. Many times people look at that now that the demand has increased, instead of putting money to build a separate fermenter, they can use existing fermenter and increase its capacity. And it's possible to do that. Overall, you're looking at increase in production yield. These are actual numbers in the plant. You could do better than this. 30% plus productivity, 10% yield. There was one company I was dealing with. When I mentioned that number, they said, even if you give me 0.5% increase in yield, they'll be shocked to death. And we can do that up to 10%. So this is possible with pure oxygen application. Better control on oxygen dissolution. There was a case where one of the company basically said that's not possible. It cannot be done. So we said, okay, let's do pilot plant. And when we did in the pilot plant, the moment he put that, he was shocked. So what it comes down to is unless you try it, you don't know what happens. And basically it follows the principles. Higher dissolved oxygen level, more efficient use of pure oxygen, less foam. That's another part also. Many times in operations, you have a lot of foam being formed because you're putting so much air to increase the oxygen concentration in liquid phase, and it end up being a lot of foam coming on the top. And many companies use anti-foam agents, which are expensive. This allows you to basically eliminate the foam. And we have done that. And as I said, in Midwest, I talk more about Midwest because we are in the Midwest region. There are companies who are basically eliminating foam, which quite a few $100,000, by the way. When you look at low capital outlay for new fermenter and reduced power consumption, with this, you don't need that much agitation also, strictly because concentration gradient allows you to quickly go into the liquid phase. And we were able to reduce the power consumption in, particularly impellers, close to more than 30%. I want to quickly jump into different areas as to where these gases have found its use. Sewage, processed water treatment, oxygen, ozone, carbon dioxide are widely used. Drinking water surface processes, again, these things have found home in there. Oxidation, high temperature processes, oxygen has found its home and to improve the productivity and yield and environmental areas. Also operational safety, repair area, and extraction pressure applications. These are wide applications, by the including pharma and biotech area. You probably have seen these slides which are used in CM2C. If you look at here, where carbon dioxide is used in applications, extractant, mineralization, chemicals. These chemicals are made from carbon dioxide, refrigerant, miscellaneous applications in metal casting, medical oxygen respirator. Then you look at blanketing inerting area, fire extinguisher. Polycarbonate and polymers are made from CO2. If you look at that anhydrous oil RICO in all these areas, again, CO2 finds its home. Food industry. This is widely used, by the way. And also biological conversion, algae, fuels, and food. These are all different areas where CO2 is widely used. And again, depends on its application, it controls the economics also. CO2 is also used in pH control in the wastewater treatment and other areas. Typically, people will use hydrochloric acid, sulfuric acid to control pH value. But when you look at the CO2 area, CO2 is a mild chemical, and you don't need that much maintenance cost associated with acid because it's not dangerous compared to sulfuric acid and hydrochloric acid, which requires proper handling. Also, no overshooting. It allows you to control your pH control much better. Overall economic benefits, this was done for one client, but I didn't want to put the numbers because that was more reflective of their operation, much better economics here. We look at the sewage and processed water treatment area. You can look at oxygen has found its home in BOD, that's a biological oxygen demand, BOD control. We have found that it allows you significantly to increase the effectiveness of the organisms and allow you to perform what you need to do in the wastewater treatment processes. And also, just to show you this example, this is called Biox hose. This has less than 10 micron size holes, and it has a flapper on it. So when you put oxygen through that, pressured oxygen allows you to open up the holes. Now you have bubbles less than 10 micron size coming up. Smaller the bubble size, easier it is to dissolve in the liquid phase, and your dissolution level is very high. And depending on the depth, you can go 8 to 90% oxygen dissolve in the liquid phase. This replaces your aerators, by the way, and maintenance is close to 15 years. You don't have to replace that, and it works really great. Again, when you have a problem with nitrogen elimination issues here, you do into two steps. So one step is basically oxidation. Other one is antioxidation step, denitrification step, where you have presence of oxygen in the first case, where you convert ammonia, will oxidize to ammonium nitrate here, and then when you denitrification zone, where you basically convert into from nitrates to nitrogen and oxygen. This is done also in the industry. If you look at many times wastewater is traveling for long distance. When you have the piping for the long distance, you're bound to have anaerobic condition where you have absence of oxygen leads into hydrogen sulfide. That in water will make sulfuric acid and will cause will destroy the concrete piping by causing more corrosion and stuff like that. In this case, if you supply a certain amount of oxygen, you can prevent destruction of the concrete pipe if it's a long distance. When you look at the boiler water, they have some requirement also maintaining certain dissolved oxygen level. They use hydrogen to remove the oxygen from the water dissolved oxygen side. Treatment landfill and ozone, many times there are AOX, which is adsorbable organic halides. They're very difficult to break down. oxygen allows you to do that, ozone allows you to do that, or UV radiation. This is also practiced in the industry. And many times, many organic pollutants are very difficult to break down, so you can go with ozone and break it down. If you look at neutralizer CO2, we just looked at that, also supercritical CO2. That is also widely used in the industry. If you know, in tobacco, to remove the nicotine, there was many, many years back, we had done that. By using supercritical CO2, you can remove the nicotine, dangerous chemicals from tobacco. And it's used now in the pharma and biotech industry also. The primary reason there is to, as an alternative, an environmentally safe operation, they use supercritical CO2 to basically sterilize the drugs. And then you have CO2 coming out, which is environmentally friendly compared to other alternatives what they have it. Drinking water and surface water area, you're looking at again oxygen, pH control, raising hardness, and also cracking for certain organic, basically viruses and germs. You can break it down with ozone and UV. Some of the other applications we are looking at, you're looking at oxygen high temperature application. When you make sulfuric acid, you're making sulfur dioxide and sulfur trioxide. If you use pure oxygen, and that is done in the industry also, it allows you to be much more efficient and produce a lot more product. Sludge incineration, I'll show you some slides soon. Also from the safety point of view, they use nitrogen and CO2, inerting a closed and open system. In the petrochemical industry, nitrogen is used widely also. Pigging and pipe inspection. While operation is going on, they want to clean the pipe and take operation. They will use nitrogen basically to blanket it, inert it, and then work on it. As I mentioned about supercritical applications, conventional application for extraction of natural products, you're looking at, you might be familiar with that as to laundry industry. They replaced their freon-based chemicals to supercritical CO2. They use supercritical CO2 in their dry cleaning and laundry-based operations. Atomization and crystallizing process with CO2 and Lin, that's also well known in the industry, particularly in the metal industry, they use that widely. This probably will be interesting to know as to many times in an exhaust system, you have undesirable chemicals going through that. And EPA won't allow you to do that. So what you see here is to those organic chemicals based on their boiling points, you're able to liquefy them. So exhaust goes through the cryocondenser. You have liquid nitrogen goes through a heat exchanger. You have an intermediate fluid here going through that takes the coolness from here and maintains the desired temperature here in the exchanger such that that gas, which is not acceptable by EPA, is liquefied and it condenses out. And now we have environmentally friendly exhaust coming out. This is the solvent recovery system. It's used widely in the industry also. They supply liquid nitrogen, and you have a heat exchanger here. An intermediate fluid will allow you to cool down the exhaust and remove the condensate. To summarize opportunity in this particular area, you're looking at economical way to increase environmental loading, handle environmental loading, and also improve safety, reduce organic emission, reduce maintenance and operating cost. Remember, for when you use these gases, you don't need any kind of compressor or pressurizer, because typically when nitrogen, liquid, oxygen, and argon are stored, they're stored in the liquid phase. So when you go through liquid to gas phase, you're looking at close to 600 to 700 times expansion in the same volume. So you have a pressure close to 150, 200, 300 pound pressure, whatever you want. So you can control the pressure depending on your needs. So you can put pressure regulator and take care of it. So you don't have any moving part here. That's the beauty of this whole thing. No backup needed, because you're not depending on any electricity here, because nitrogen, oxygen, they have a desired pressure, what you need. So in case you have power failure, the system is still operational here. That's an opportunity for economically expand the load handling capacity. You are looking at also economics is reducing energy. It not only improves the efficiency, but also impacts the maintenance and operating cost. For a case like this, as I mentioned, 15, 20 years, this stays as it is. There is no changes to EPDM plastic material, by the way. And then very effective to meet BOD and COD requirement, biological oxygen demand, chemical oxygen demand. Now quickly look at the high temperature application area. Again, this is a retrofit. You don't need to change your furnace or anything like this. You can control the temperature based on how you apply the system. This oxygen is controlled through control panel, which typical industrial gas company will supply to you. And also oxygen speeds up combustion. I'll show you why it speeds up in a minute. And also there are safety features in the control panel that when the demand is reduced, automatically shuts down for any unforeseen conditions. And depending on the technology, there are various ways to use oxygen called oxy-fuel burner, enrichment, injection, all these different technologies, they are found home in these kind of high temperature applications. And very easy to operate. Once you set it up, you can operate that and very reliably operate that. One of the reasons why they use oxygen. This is a case where you have 21% oxygen in air. That's the air. When you use air-based combustion system, you have, let's say, 100% your flue gas coming out. As you increase your oxygen concentration in the air, this is 25%. The way you do is you back off an air and put pure oxygen in there, such that you have 25% oxygen concentration in the air when you're using combustion. You can see you reduced your nitrogen, and that leads into the lower exhaust. 50%, 100%. When you totally eliminate your air and put only pure oxygen, look at what has happened. You don't have any nitrogen. So you have the CO2 coming out here, and you can see the total volume significantly low, and basically you don't have any NOx emission either. So this is the reason why people use pure oxygen in combustion processes. Allows you to environmentally control your total volume. Imagine if you have already cleaning system for environment, how efficient it will be working. Also allows you to capture CO2 because it's much purer CO2 and utilized for other purposes if you have to. This is another reason why this oxygen works. If you look at here, this is the percentage oxygen which you put in the airline. When you put 100% means there's no air. And there's a pure oxygen added to airline. And this is the flame temperature. This is the temperature in the middle of the flame. When you have natural gas, and this is the natural gas and air, you will see the flame temperature 3,400 degrees Fahrenheit. As you increase your oxygen content, oxygen concentration in the air phase, you can see the amount of, the flame temperature keeps on going up. When you have pure oxygen, you have 5,000 degrees Fahrenheit temperature. What does that mean? When you look at the flame temperature going up, that means your heat transfer moves from convection to radiation. T to the fourth power, if you remember your equation. So you're transferring your heat much faster, much easier when you have 5,000 degrees Fahrenheit temperature. You have to control and look at the, your furnace, how you're using it, and you want to make sure it's safe to use it. But we have done this in so many applications. It's very successful. We have done that part. If you look at the typical furnace, maybe cement industry or lime kiln for pulp and paper industry or coke manufacturing operation, you will see the big furnace. You have a refractory lining, and you have a main burner, which is typically natural gas, air, or coal and air. But you have this kind of flame, and if you look at the temperature in the middle, will be somewhere around, for natural gas, will be 34 degrees Fahrenheit. What we did is we used oxygen lamps. So right underneath the bottom of the flame, we basically made oxy-fuel flame, much higher flame temperature here. So what it did is to, in this part, your heat transfer converted into radiation heat transfer. And here's the product. That's how they do that, cement industry, lime kiln, all different industry, coke. And allowed you to very effectively produce the product what you're looking for without impacting the refractory lining. Since you have here cover on the top, but the flame temperature is only 34 degrees and this is 5,000 degrees, so this refractory did not see any high temperature. And again, you have a product here. So product captured most of the heat, what's needed. If you look at the side view here, you're going to see that this is where the opening for the lance and different positions as to where you put the lance. But this is called undershot method. It's used in the industry also. This is a typical incineration system. Where you look at here, typical incinerator, whether you use waste liquid or similar to that, they will have a primer combustion chamber where you will put the pure oxygen here in order to burn as effectively as possible. And then, even though there's a leftover incomplete combustion, you will see a lot of CO, carbon monoxide, coming in this area. So you put pure oxygen here also, convert CO into CO2. So by the time it comes out, it's all CO2. I had the pleasure of working with DOE in Louisiana State. I was working with a very big chemical company, and they had an issue with emission. And I put the system like this, and they were all shocked. And they invited me to their office, and we made a presentation to so many inspectors as to a system like this could work, and it's very economical. Rather than shutting down the facility, you can operate this kind of system. You can look at this. Applications are wastewater incineration, spent sulfuric acid, black liquor oxygen. This is for pulp and paper industry. Soil decontamination, Klaus process, that's sulfuric acid. CO post incineration, what you saw here. Incineration of sewage waste, liquid waste sludge, liquid oxidation, and special waste incineration. So these are all different industries where high temperature application using oxygen. Again, excellent way to handle increased environmental loading, increased combustion efficiency leading to high productivity and flexibility. Improved safety, increased flexibility, reduced CO emissions, significantly reduced exhaust volume. Excellent way to reduce exhaust, because many times when you put too much air, it does impact your exhaust volume and affects your cleaning system. Now we look at quickly wastewater treatment area. What you see the picture here, that's what this is. So you can see that how it produces, bubbles, and bubble size does affect the dissolution. Smaller the bubble size, more the surface area, easy it is to dissolve. This is a typical plant where this has been used widely, and it has, as I say, 10, 15 years, you don't have to do anything on that. Why does it work? If you look at water and air, under ideal condition, you will have 8 ppm of oxygen dissolved in the liquid phase. When you use pure oxygen, went up to close to 40 to 40 ppm, and then in the same ambient conditions. Now, if you increase the pressure, you can go further. At 100 pound pressure, you will have dissolved oxygen 100 plus. So again, it depends on your needs, requirement, how much oxygen it is in the liquid phase, and how you can control it. Liquid phase reaction depend on the DO and water. And that's the whole idea. If you look at in the liquid phase reactions, only thing which are dissolved in the liquid phase, they work. Other gases will just come out. So if you have too much air going in, you're going to see that, if you don't have high RPM and if you don't have a lot of mixing ability, a lot of air is going to come out. When you use pure oxygen, if you put too much oxygen, you're going to lose oxygen also coming from the exhaust, from that. But you have to control the amount of oxygen going in, and you can cut down your basic turbulence or Reynolds number, and you can basically impact your performance. Remember, oxygen does cost money, but by doing this, by controlling oxygen usage and to your needs, you can easily control the oxygen cost. Applications you find in the fish farming, fermentation, pharma industry, wastewater treatment area, all these areas where these gases, oxygen is used. For example, I just quickly went through this. Under 1 atmosphere pressure, this is a trend. Depending on the temperature, again, higher the less dissolved oxygen. Lower the temperature, more dissolved oxygen. You can see that that's a pure oxygen, and this is air. When you look at high pressure, depending on the pressure what you have, 80, 90, 100, you can see that your oxygen concentration in the liquid phase goes up high. If I summarize and compare, in particular wastewater treatment area, various applications, this is the one method to supply oxygen in the liquid phase. This is another method, and this is another method. These are relative numbers together. This is a medium, high, very low. So you can look at that. The capability what you get is Biox host system. And versus selector. Remember these, you're looking at power usage. That's what you have here. Where here there is no power here. And you're looking at the maintenance part. That's not included in this part, which makes it very expensive processes. Benefit, again, summary for wastewater treatment area is low investment, high oxygen efficiency, no energy consumption, easy to operate, maintenance free, immediately ready. When I say no energy consumption, it refers to basically amount of oxygen, going into the aeration related efficiency you're looking at. High availability, noiseless, extendable, high flexibility, no odor problem. Remember, when you use too much air in the wastewater treatment area, you have a lot of organics coming out from the wastewater. It will create, the environmental issues. I had a case here, right here in Midwest, that every time they put a lot of air and you had a waste with organic load going in there, the neighbor will complain, hey, it's smelling too much, it's too much odor, do something. So that's why ever since we put the system in there, no complaint at all. Because it allowed you to create an oxidative environment, so there was no hydrogen sulfide, which causes the odor, by the way. That was totally eliminated there. Fish farming, that's another, some of the interesting things here. This is in aquaculture industry. You can look at that. I did some work in California where for fish farming industry, they had a problem with occupation density for the fish and also the demand for fresh water was very high. When we went there, we were able to, in given area, we were able to increase the density to more than 100 kilogram per cubic meter. Fish will, during the time when you feed them, that's when they need oxygen. When you feed fish, at the time they will start running around. The primary reason running around is they want to get more oxygen. So they get more air through the gills and separate oxygen and take the oxygen for your carbohydrate conversion to energy and CO2. If you don't have it, then fish will die. So and what we did with this is when you put oxygen, they did not move that much. And they grew significantly high in short time in their weight. And they were very healthy. They had they were high resistant to disease because they were very healthy fish. And that was done. People are using in industry that approach too. Again, that goes down to DO level. Anytime you look at the liquid phase, DO is a very critical part. It's all oxygen. Now I want to quickly touch on this. You're going to look at this tool. Technology Solutions Incorporated has developed the tool, which is used in the industry for a variety of reasons. This particular tool is antibacterial, spark-free, and also unidirectional. Many times in the lab, when you particularly, I'm talking about lab here, when you use your cylinders, it's very tightly closed because you are afraid of leaking and things like that. And then next time somebody wants to open it, it's very difficult to open it. This tool allows you to unidirectionally open the valve and allows you to very easily, it opens up very, very easily on that. Also the question was if you use on CO2 oxygen cylinder, again you're worried about spark-free. This is a spark-free wrench which allows you unidirectionally. Now if you're working on biotechnology or pharma area, you have organisms, you have bacteria. You don't want bacteria from one place to other place to go when you're doing something. So this is antibacterial spark-free unidirectional wrench. This is introduced in the industry not too long ago, and we have found wide application not only universities but also in the pharma and biotech company. So something for you guys to see it. If there's an interest, there's also a brochure there. And the other version is carbon steel, which is not spark-free or antibacterial. But EPA states that if you have copper content more than 58% in your tool, it will kill bacteria. And this is more than 58% copper content. And that allows you to be qualified as a antibacterial. This is operation, how it's used. You can see that here's the cylinder, the wheel, and the wrench sits right on it and just opens up. So very easy to open it. There are two holes on the bottom side. Right here, those two holes are, one is for medical gas cylinder, other one is for welding gas. Unless of a whole healthcare industry, this does allow you to open and close the medical gas cylinder, or you can weld gas cylinder. So that feature is added to that. This concludes my presentation. I think I'm on time, right? It's okay. Any question, then I'll be glad to answer the question.
Yes, we'll first take if there's questions here in the audience.
I know that supercritical CO2, it can replace a lot of organic solvents. So what's the challenge right now? Is it using supercritical CO2 in those processes, or is it the cost of the solvent that inhibits in those supercritical?
Depends on the process. If you have an expensive chemical which you're making, when you use this CO2, it's easy. Pfizer is doing this process right here in the Midwest region. So it is applied, and then when it's going to increase its usage more and more. So again, what chemical are you separating? What is the final objective? If it's sterilization, you'll find that it is very interesting. We can probably use that. If you're using for different chemical extraction of different chemicals, then depending on what chemical, what value it is, that's a function of how valuable your product is. Okay.
Very, very interesting presentation.
Thank you, sir.
What especially struck me is your discussion about the aquaculture. Mm-hmm. And you indicated when you increased the oxygen level, you said the fish grew, but they weren't as active as they were in the past.
No, they were not running around to look for oxygen in the liquid phase. They were very happy, healthy, moving around. Since they were healthy, they were resistant to disease. And second thing is, food, what they ate was converted into desired quality. They wanted more, energy that happened and CO2 coming out. If you don't have sufficient oxygen, they will run around and they will use a lot of energy, so they'll become thin and thin. Here, that allowed you to do that.
Yeah, and I was wondering what the advantage was of not having them go around. But
right,
what you're
right,
saying
right,
is
right.
then.
And sometimes they die too in that processes, and we found many dead fish.
Oh, interesting.
So by having that, if you have ample food available to you, and if you do normal activities, you don't have to go out of your ways, you'll be healthier and do better things. Same thing in fish. And they were able to sell more fish because they were growing much faster in a shortened time, and they can sell the fish. That's what they were doing it. Thank you.
We'll take a couple more questions here.
I wanted to know if you have any thoughts or solutions to the impending helium crisis we see in the next 20 years.
The answer to that is I've been through that phase in 2013. There is alternative hydrogen, using hydrogen alternate media to replace the helium in some of, particularly if you look at GC and some other places where they use helium, they can use hydrogen that too. But I think in overall picture, again, overseas market as to how you can bring the product here and that kind of stuff. But it's an international thing. It's not just a U.S. It's a global requirement, global thing. Yeah, and I don't have any better answer than that.
From online, Rob asks, isn't oxygen expensive?
Good question. Oxygen does cost money. Depending on the volume, depending on how much oxygen you use, that's what will lead to cost. Larger the volume, less the cost. Less volume, more cost. It can range from, industrial gas company talks about 100 standard cubic feet, as a measure for the volume. When you use, let's say, 100,000 cubic feet per month of oxygen, you're looking at oxygen price somewhere around 40, 50 cents, depending on how far the air separation unit is. If your requirement is at 5 million, 6 million, 10 million cubic feet of oxygen per month, you're looking at maybe 20, 30 cents oxygen cost. That's the typical cost. Again, depends on the distance from manufacturing site and the volume. There's two parameters because there is a shipping charge moving oxygen or nitrogen from the manufacturing site to the use point, and cost of manufacturing. Electrical cost also in that area. Yes, sir.
My question was, do you know if the use of pure oxygen in wastewater treatment has any impact on bulking sludge or filamentous bacteria? So you mentioned it does have some effect on different communities.
It does.
Does that make it more or less or about the same?
Mixed liquor suspended solid, MLSSV, you're looking at, that will significantly go up. Why is it? Because your organisms are healthier, and you will see a lot more activity in COD and a BOD conversion. I have the chart I will share with you later on this, and I'll give you that information.
Oh, very interesting talk. You know, I saw you have a lot of application. So I wondering, you mentioned for the soil decontamination.
Soil decontamination, yes.
I just wondering, do you have a kind of this case to work on it?
It's already done in the industry. We are doing that in the industry. It's done in Europe big time. You go deep inside and you supply oxygen to really activate the organisms and decontaminate that way. That's a one application. If you look at the St. Louis, you might know Wentzville. It's a very famous place where it was classified by EPA, where they had radioactive material in there. And they basically detoxified that by using incineration, oxy-fuel burner system. You had a much better, combustion and got rid of all that stuff. It's all cleaned up. So yes, that's done in the industry. It's not new. And it basically, the way decontamination is done is you supply oxygen way deep into the soil and basically remove that. Yeah. Okay,
I have another question about the fishing pond.
Yes, sir.
Usually I know that for the fishing, you pump the oxygen in the pond, but usually water DO the value about A is, for my understanding, is the best way for the fishing. But something like you pump more oxygen, the looks better for the fishing group. So do you think the highest would be better? How high? It should be have some
there's
the value for the DO.
I can answer that. Yeah, the maximum oxygen you can dissolve if you're pure oxygen without pressure, I guess it's about 42 parts per million. You can't go more than that. Depends on pressure and temperature. If you're deeper, it will be more. Right on the surface there. Fish, when you look at during the feeding time, the DO level is very low, because fish uses most of the oxygen. That's the time you don't supply all the time. During the need time, you supply oxygen. So when they need oxygen, you supply oxygen. And that is certain period of the cycle, day cycle, that's when you supply. You don't continuously, because it becomes expensive then, because you want to utilize oxygen most effectively. And the way to do is when the feed time comes, supply oxygen and you monitor DO level. When the DO level is low, 1 or 2 ppm, that's why it goes down to very low, sometimes 0. When you go that lower, you put pure oxygen in there. So you have to figure out your cycle time when the oxygen requirement is very high. I myself have done it for some of the other fish, and then we set up the cycle. When are they going to feed? Because that's the maximum time where they need a lot of oxygen, and supply that time oxygen. You don't continuously do that. I hope that answers your question. Yes, ma'am.
Thank you for the interesting presentation. My question is, for the oxygen application in the combustion area,
yep.
You mentioned that the temperature, when you substitute oxygen with air, the temperature goes up to 5,000 Fahrenheit.
No, not temperature, flame temperature.
The flame temperature. I know, but wouldn't that still be very high? I mean, I wonder how many current power plants are able to handle that temperature, because if you consider the cost you need to substitute the entire process, that would be very, very expensive.
To answer that question, oxy-fuel burner is widely used in the industry for NOx emission. California, when the NOx emission came into play, they switched from air fuel burner to oxy-fuel burner. What happens there is your flame temperature is high, so the heat transfer is increased significantly. So you back off in fuel usage. So if you're using 100 cubic feet per minute of natural gas, you go to 30, 40, 50 cubic feet per minute. So basically you want to adjust your total heat input, total energy input as your control. The goal is to increase the heat transfer, not to maintain the high temperature. But high temperature allows you to transfer heat through radiation heat transfer. And that's the benefit you look at. You don't put the same or natural gas, otherwise there's no benefit. So you want economics point of view, cut down the fuel usage and maintain the same production, because now you're able to get more heat. Does that answer your question?
Yeah, I was just wondering if the business can do that.
Oh, they would. The way it's done is, as I said, the goal is to increase the heat transfer to the product. So you back off your gas input. And by doing that, you're taking the total source of heat away. But whatever you're putting in, you're making maximum impact on the product. That's what you're doing. And you want to make sure the refractory, normal refractory, is able to handle up to 4,000 degrees Fahrenheit, whatever the temperature is. So you, based on that refractory, you adjust what kind of oxygen use you can make, whether it's enrichment level or pure oxygen. You may go to enrichment level probably, or the lancing on the bottom. So you're able to control your exposure to the refractory to some temperature. So again, it depends on the process, depends on what you're looking for at what end, and then I can be more specific if you know what you want me to do. Okay. Yes.
Thank you for the presentation. Two aquaculture related questions. One is that in the example that you gave, the production density was about 100 kg per meter cube. So often species at that density, I mean, I'm even thinking of like 75 kg per meter cube. There is a lot of, intense fighting for the food, and
right.
also, that often leads to some amount of, infighting, and also there is the more increase in ammonia being generated because more of the fish is utilized for food. So
yep.
How do you balance,
okay.
Because ammonia is so toxic to the fish?
It's a very good question. When you have high density in the fight for the food, once they fight for the food, they want to digest the food. So the demand for oxygen goes up significantly. Okay, so when you provide sufficient oxygen, they will be happy because the food is digested quickly. And also having, as I mentioned before, denitrification, nitrification step, we have aerobic and anaerobic condition. Having supply of proper oxygen, you will not see that. You will avoid that, because we have seen in the given volume, when you supply pure oxygen, the population went up further, but they were still healthier and very well maintained. And depends on the raceway, how that is set up and what it is. But no, I have not seen that kind of impact on that. Okay, thanks.
Are there any other questions here from the audience? Okay, well, we want to thank you again for your presentation this morning. Thanks.
Thank you very much for allowing us. And I hope in your work, probably something like that might help. And I'll be glad to help if there is any need in this area. But my goal was to share with you as to what's done in the industry. Industrial gases, oxygen, nitrogen, argon, these are so valuable chemicals. To me, they're chemicals. How they use in the industry, variety of industries. You might be working on the different projects. You might find a home for that. So it's up to you guys how you want to do it. Thank you very much again. I appreciate that. Okay. And if you want the brochure for the ranch, if you want to see the bioxos, it's here. And here's my contact information. Karen is a key person for contact, so he can tell you about that. Okay. Thank you very much again. Appreciate that.